So welcome everybody again to the Escape Summer School. We are back from the coffee break, and we have again Tom, and this time he will be introducing, going very deep into Numpy and explaining this nice library and all its functionalities. So please, Tom, whenever you want, go ahead. Thanks.
Okay. Yeah, I think we can go ahead. So this is the first time I do this introduction to Numpy non-interactively. So we try our best to make it still a bit interactive in the sense that you can somehow communicate to me. So I make it interactive in the sense that I'm working in this interactive notebook. But whenever you ask questions, just post them in Slack, and the other guys will, the other people will try to pick questions and pass them to me, so they can interrupt me, and then we can talk about your questions also in this notebook. So if you have, I just uploaded, Thomas just merged the latest versions of this notebook. So if you do a git pull, you will see a few new files in there. Let me show to you how it looks like. So this is the directory structure. You will see these files here. Numpy warming up, the exercises, nearest points, and binary data. So these are the 4 notebooks we are working with. These solutions are not committed yet. I will put them later on. So you can, if you want to, if you are bored because you are more advanced, you can just skip to the exercises and nearest points and binary stuff and explore those, or just follow with me along. So, okay. Then I switch back to my agenda, and let's start. So I opened a new notebook, so feel free to open a fresh one. You don't need anything. You should be able to follow me. Whenever you are lost, occasionally I have some checkpoints where you can just catch up again and just type in the command I'm typing, and you will get back. So I'm not using things from the first cell in the 100th cell or so. I usually start with printing some versions just for future reference, and I also initialized here the random number generator. So whenever I will commit this live session also to the repository, it will contain basically everything which is in warming up, exercises, nearest points, binary data. But it's live session, so whatever you have asked, then it might land here, or extra explanations which I don't have in these notebooks. But as I said, I will relaunch everything with this number generator. I will use this all the time, so everything will be reproducible and the same in future. So I'm running here Python version 3.9.4 and NumPy version 1.20.3. This is coming from the CondaForge environment, which you have already installed, hopefully. If not, you can use any kind of NumPy version. Really, this should work with the recent ones, also with older ones. So I'm not using any fancy stuff here. Okay, so this is the first cell. Let's execute the second cell. This is a Python magic I like to use in my presentations when I'm working with Python. This just introduces a new magic, because whenever you do something like this, which throws an error, in this case it is really short, but sometimes it's really, really long because it prints a stack trace. I can use this magic to just print the short error cell magic, or it doesn't work. Yeah, that's why I love live coding. Let me see, did I make a mistake there before we start? And someone did not register it. Oh dear. Okay, you know what? We just go ahead. I will figure out. It's for now. I will not use this, so you will see long stack traces when I encounter an error. Okay, so let's start with NumPy. So we imported it as np. This is our module. It lives in this directory, and in this case, and we can really start off with the array type, which is our main thing to work with. So there is this constructor called or this function called NumPy array, and if you pass it just a few numbers, you get back this array. So let's store this in a variable so that we can inspect it later. So if I print it again, I can actually also print it like this, then it will show it in another representation. If I just put it in the cell and hit enter, it will report the last expression returned by the cell that you probably already know. Let's look at the type of this A. You can see that it is indeed, this is this ND array type, and it has some properties. So I try to be slow and then type a little bit of things so that you you can follow along. So these are the array properties. Let's make it a bit bigger, like this. So it has a size, and this size gives you the number of elements, and it has also dimension. In this case, the number of dimension is 1. So this is how you can inspect this thing. And I also talked about the shape of an array. So you know that Numpy arrays are rectangular, but they can have multiple dimensions. So in this case, the shape is a tuple of containing a single element, and this is then basically also the size. So whenever I create another array which is multidimensional, the size will give me the number of elements, and the shape will be then containing more numbers in it. And I told you that this array is now stored in memory. So these numbers 1, 2, 3, 4, 5 are sitting next to each other in memory, and they need a specific data type. This is called dtype. And the way it's stored in Numpy is it's attached to this dtype attribute. So if I call this, you can see that these are now integer 64. So if I create another array, let's call it also A, array, and I pass in some numbers which are obviously not integers, like this. These are now 3 floats, and I examine the dtype. You can see that these are now indeed float 64, which is the default float type on my machine, because I'm using 64-bit machine. 64-bit machine. Okay, let's have a look at multidimensional arrays. Let's construct one. Let's call it B. Let me write it so I have some time to recover from this information overflow. Multidimensional arrays like this. Okay. So we use the same constructor like this, and now we can. So if we use this list, this is now a single dimension, and we can nest another list in it like this. So now we have our multidimensional array. As you can see, this is now represented by nested parentheses. So let's look at the size. The size is 6 because we have 6 elements, and the shape is now represented again by a tuple, and these are now 2 entries. So we have 2 and 3. This means that in the first dimension we have 2 elements, namely the 2 subarrays, and each subarray has 3 elements. And as you may recall, I told you that with Numpy it's not really possible to do something like this, and this is what you get. So I now passed in 2 subarrays which have different lengths. So now I'm not in this rectangular thing anymore, and this now complains that it cannot be, but it contains reg nested sequences, and you can see that it now has this dtype object, which means that it now falls back to Python objects. So you don't have this contiguous memory thing anymore. This is now really an array of lists, and this contains the pointer to this list, and the lists are containing these elements. So now you cannot do nice operations on them anymore in a high performance way. So don't do this. If you need something like this, you really have to use something like awkward array. Okay, array methods. So we have now created some arrays. Type in array methods. Let's look at some methods which you can call if you use arrays. So if we look at our A array, if I hit dot and then tab, you get a tab completion in Jupyter, which is really nice. And there you can see that there are a lot of methods you can pick from. And we can, for example, have a look at min. Call it because it's a method, and this will give you the minimum, basically the lowest value of it. There's also a nice thing you can discover if you hit Shift Tab inside the parentheses. This will give you the doc. This will give you the doc string of the function. So you can see that it also takes different parameters, which are for now not so interesting. But if you look at the second array, which, if you recall, is this multidimensional array. you can see that it picked simply the lowest value of all elements. So it iterated through all elements. But maybe you're interested in the lowest value in each dimension or so. So let's have a look again at this min function. So again, I hit b.min parentheses, and then I hit shift tab. And there you can see there is this option called axis none. None is the default value. If I choose axis 1, it will call this method on the first axis, on the second axis in this case, which means basically do the operation on each subarray. So this will give you an array with each with the lowest element in each with the minimum element in each axis. There are other nice things which are useful, like sum, which just sums on all elements, and also here you can use so axis 0 will sum the elements over the first axis, and the axis 1 will sum the elements over the second axis. So depending on what you need, you can configure this. This will be very useful later, of course, if you work with multidimensional things. If you work with just single arrays, it's not important at all, of course. Okay. Now that we have some arrays, we can do some operations on them. So in case you have missed how to create A, I just recreate it. So array A was array 1, 2, 3, 4, 5, 6. And let's subtract something from it, 42. As you can see, Numpy already knows or figured out what I wanted to do. At least this is I wanted to do. It now subtracted 42 from each element. So this is what you get back. This is also an Numpy array, and it's type stable, and yeah, all the operations are done in a performant way. And you can even do a combination of these, and it will always figure out also the right type. So as you can see, here I divided by pi. Here I'm using the constant, which is defined in Numpy, and it figured out, okay, now you want to have some, now you need something like a float to represent the results, so it automatically converted the values. Here you can see that these are integers, and as I said, these are floats. Yes, there are other things which you can do, like the power function, like a to the power of e, and it also works the other way around, of course. So you can really work nicely with it intuitively. It's an element-wise multiplication, so you have to be careful whenever you want to work with stuff where you expect something different. So this might remind you of something like a dot product, but in this case, it's really just element-wise. There's also another operator, which is this @ sign. This was introduced in Python 3.5. So if I use this, this will now do the dot product. If you don't like this @ sign for whatever reason, you can always use the dot function of Numpy, which is a helper function to do the dot product. And what you also can do is operations like less than or equal or whatever. So for example, if I do this, and this will be very helpful later, as we will see, it will create a Boolean array, which contains an entry for each value. So for each value which is less than 3. So you can see the first 2 are true, and the following 3 are false. The same is working if you do this with the equal sign. So here you can see the only value, which is 3, is the third one. And you can even combine these things together with binary operators. So if I want to do something like it should be greater than 3 and less than 5, then it looks like this. So here it's important that you don't use this and operator, then you will get an error, because there is the syntax is not working here. So it's a binary and. This means that basically both parentheses are evaluated individually, and then the AND operator is performed on each element pairwise. This is very useful if you combine so-called masks, which we will discover later. Okay, so let's have a look at indexing, basic indexing, slicing. which is a powerful tool to rip your data into parts. So we have this array A. For everyone who has not created it yet, let's recreate it again quickly. Got this. Okay, this is how I made it. The 0th element is 1, so this is how I index it. I just tell it whatever I want, and in this case, Numpy is indexing starts with 0. There are other languages which start at 1, like Julia, just in case you are wondering. You can also use the minus notation if you want to count backwards. So if you put in -1, it will give you the last element, or -2, then it will give you the second last element, etc., etc. This is very useful if you just want to have the last one. There are also so-called slices. This works quite similar to Python. The syntax is basically start, end, and step. Maybe I put it as a comment here so that you know what I mean. So I can, for example, say I want to start at index 2, which is the 3rd element. The end should be 6, which is in this case the last element, and I want to step in, the step size should be 3. So this will give me 3 and 6 and then stop. This is how you can create sub-arrays or subsamples, for example, if you need that. There's also a nice trick, so you don't need to provide the start and the end. You can just omit them. And if I say that I want to step backwards, then you will just reverse your array. And this is a very useful thing if you need to quickly turn the array, or reverse the array for whatever operation you want to make. And if you recall the B array, which was created with this nested thing, B array, 1, 2, 3, and 5. Oh, it's a bit ugly. Sorry, I'm a bit. There's a typo. So this is how we created it. If we do now something like reverse, then you have to be careful because now it's reversed along axis 0. So keep this in mind. You want to always be careful on whatever axis you are operating in when you are doing slices. Okay, so let's discover this. Indexing, slicing in multiple dimensions. All right. So let's create a bigger Numpy array. I hope you can follow along and it's not too fast. We had recent complaints about being too fast. If it's too slow, then I'm sorry, but I think there are people who are, if you're bored, as I said, you can open the exercises and work on them and skip this introductory part. So there is a
For the moment, there is no comment, so I think it is going smoothly. Thanks,
okay.
Tom.
That's fine. I forgot the comma. Thank you. Okay, so this is my B. I just recreated it, so feel free to type it down. So multiple dimensions can also be sliced quite easily. There you separate the slices you are interested in with commas. So in this case, if I do it like this, I get, so 0 means take the first element. So this refers to this first subarray, and 2 refers to the third element of it. So I get back this 3. I can also put in more fancy things like, for example, give me from the first subarray the elements 1, 2, 4 without a step. So in this case, all of them. So now we have received this part of the array, as you can see. And let's do an example with a step. For example, 0, 1 to 4, 1 to 5, and steps of 2. So now you get these 2 and 4 because you started at the second one and steps of 4. Okay. Another thing is which you see a lot is this double column operator, or let's call it operator. This will select everything on this axis, and so if I do something like this, this means that from each subarray, so these are my two subarrays, I want to have the elements 1 to 4. So in this case, I sliced it so that I received only this piece and the second piece. So this you will see a lot when you are dealing with this kind of stuff. And of course, you can also have a quick look at the reverse trick. So if I do this, I reversed the array in both directions. So the places of the two subarrays has now changed, and also the direction of each array has been changed. So this is how it works then. Okay, so let's have a look at some advanced indexing. Let's grab some kind of array. I call it now D array, and yeah, I don't know, 4, 3, 2, 5, 4, 5, 4, whatever. Take this example, and now we also create a mask with the same number of elements. So I put in 8 elements here. So just feel free to type whatever you want 8 times. False, 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 true, true. Is it 8? Yeah. So we created this manually, and let's store it as a mask. So I type mask in front of it. So now we have a mask. So we have this array D with 8 elements, and this mask, which has a D type of bool in this case. So in case you don't know, bool is the D type for Boolean. So it's true or false values. Okay, and if I now take my D array and apply this mask as an index, basically, you will see that it will only pick the elements which are sitting at the positions which are marked as true. So this is really cool so this is basically the way to pick elements given a set of conditions. So you may remember that I showed to you that if you do something like this, D greater than 3, you get back this Boolean array. This means that now you can also store this in a mask and then apply it to the same array and only show elements which are greater than 3. You can, of course, do everything in one step like this. It might be a bit cryptic, but it works. So this is how you can quickly do a cut on your data set. You have to be a bit careful because some operations where you think you get a Boolean back might give you instead some numbers. So let's create a mask which is consisting of digits, or let's call it ones, zeros to make it more explicit. So an NP array of 8 elements which are 0, 0, 1, whatever. 0, 0, for example, like this. If I now use this on D, so let's recall this is our D array. If I use this mask, this is now not retrieving the second element and the fourth element, fifth and sixth, but it will pick the elements at the index you have specified. So the first element of the resulting array will be the first of the original array. The second element will be the second element of the original array. The third element will be again the first element of the original array, etc., etc. So yeah, this happens quite a lot actually. What I've experienced that sometimes these Boolean masks are zeros and ones, and people are confusing them and then wondering why the data looks so weird. Yeah, because they suddenly only get the first and second element multiple times instead of the masked ones. You can use this trick to convert it to a Boolean. Oh, let me write it in a new cell just to make it more explicit. So I can convert this mask to a Boolean type, and that's interesting. Okay, I'm confused. What's happening there? Maybe I made a mistake. Okay, that's fine. It's just picking really the values of 4, 5, 4, 5, 5. It's almost the same, or yeah, it's exactly the same. Okay, maybe that's a bad example, but in this case, let's change this to 1, 1, 1, 1, 1. So this Boolean mask will now only take the first elements of everything. I have to admit this has been changed in the newer versions of Numpy, so this is cool. Forget about what I said, but keep in mind in all the versions this is the case. So okay, this is a nice discovery. So you don't have to convert it. It figured out that I'm using it as a mask. Okay. Again, what learned, as a German would say. All right. So let's talk a little bit about this dtype. So basics of dtype. So I already talked about this dtype. So whenever you create something, it has a dtype in Numpy. And you can also create dtypes by yourself. So in this case, I can call this dtype constructor and pass it something like a single char. So this will get a default float dtype, or I can pass it a D, which stands for double. And this is the float 64. Or I can also explicitly ask for something like F4, which means a float 32. The 4 stands for the number of bytes. And 1 byte is 8 bits. So this is why you get this 32 bits, or in this case, then float 64. Or if you want to have more precision, you can even go, or less precision, sorry, more precision. Go to lower ones like float 2, which gives you float 16. There are integer types, which are denoted as I. This is the default small integer. And the I4 would give you, I8 would give you then the 64-bit version. And there are also complex types. So in case you are working with complex numbers, you can use the C. C16, for example, gives you the complex 128. And other types like fixed string types like S8. This means that this is a dtype which stores 8 characters in each element of the array. So this is nice if you have to work with some kind of strings, or if you want to do text processing with Numpy, where of course text is not really accessible in high performance context. But yeah, you want to analyze words, you can pick a container where each word is somehow fitting in, and then do really cool fast operations on them. Okay, these types have properties. So if I create a dtype, then I can also specify a bit more than just the type, which is in this case I for integer. Here the 4 is the number of bytes it has, and this is now the byte order. This is basically the endianness, how the bytes are ordered in memory. You can check the byte order by looking at this byte order attribute. This is important if you are working with files on data, if you have to parse your own binary structures. So I saw during my presentation earlier this day that some people are working with custom binary formats, or many people are working with custom binary formats. They probably have to write at some point some code where they need to parse this stuff. This is why I'm showing this. This is a common problem where you have to work with all the data from old detectors, telescopes, or experiments, etc., which store their own binary formats. And they often have some weird byte orders coming from older languages or network systems where the byte order is different than your host system, etc. So this is why it's important how you interpret them. So keep in mind, whenever you read data with Numpy, which is binary, and you get weird numbers, maybe your byte ordering is wrong. So you just use then the other way around. So this automatically matched my host byte order. That's why it's showing this equal sign. Yeah, and item size will give you the size of each item in bytes. Of course, it's not a surprise that an integer 32 has 4 bytes. And you can also call a name of it. So it will display it nicely if you want to make some charts, whatever dtypes you use. And there are much more advanced dtypes, which are structured dtypes, which are useful if you want to do some nice interfaces. So as you have heard in my previous presentation, you don't want to create a class in Python like a class point and then do something like init and then give me a self x and y and then set self, I forgot this, x and self to y and then create millions of these instances of it. I mean, it's nice to use because you can pass in something like this and then access it as an attribute, and it's really readable also. But it's not performant because this is a huge blob in memory just to store 2 numbers. And especially if you want to store millions of it, you have the overhead of each of these instances. So instead, or maybe if you have even more things like the energy or so, etc. Let's put in 50 GeV or whatever. Okay, so how do you do this in Numpy to make it easier to use? So I create a dtype, and now I use the same constructor, dtype, but instead of giving it something like an integer or a float, I give it now a more complex structure. And in this case, I'm using a list. And in this list, I put in some tuples, which represent my fields. So if you are used to, if you have worked with other languages, which has the concept of structs or types or whatever, then you can see it as a struct, for example, in C. So I can say that there is a field called X, and this field called X has a float 64. And there's another field, and so I put in another tuple, which is called Y, and this is also a float 64. And then let's put in an energy, which is, for example, only stored as an integer 32 in this case. So this is now a dtype. And if I look at my dtype, this is how it's represented, exactly the same what we have put in. Now the item size will give you the size of each element. So if you add these up, you have 8 bits, again 8 bits and then 4 bits, you end up with 20 bits, bytes, sorry, for the whole element. And you can look at specific fields of this dtype. So for example, our field X has a dtype float. Then we have the field Y, which is also float, and the field E, which is now an int 32. And always be careful which kind of types you need. So for example, if precision is not so important, but memory is, which is, for example, the case in machine learning applications, you don't want to pick 64 bits, but go lower, for example, in the 32 or even 16 bits. But whenever we need really large numbers and really high precision and in higher ranges, then you need more bigger structures. So this is this floating point thing, which you can look up. There is this IEEE specification which you can read, where all the downs and ups are explained of these float types, etc. And of course, if the energy is not negative, which we assume, you can use an unsigned integer and use more of this value range even. Okay, so how do we work with this now? Before I show this to you, I wanted to show you that you can also create a much more complicated structure with this dtype constructor by passing in a string directly. So here I tell him that, for example, one field is an integer 32, and then the second has a weird shape, but still rectangular, and it's a float 64, and then, for example, a complex one. And this will now create this structure which contains one number, a small matrix. This could be, for example, a set of 4 vectors, and a complex number. So I can use this dtype to represent my arrays. So how do we use them? Let's have a look at an array, which I create like this. And as I already showed to you, you can specify the dtype. So if I pass in like something like this, like a simple array, which is containing only integers, but I say, please convert them or cast them to complex 64, then this is what you will get. So now you have an array of complex numbers. And if I now want to have my dtype from above, which is this complicated XY energy thing, I can do the same. So let's create an array with some entries. And now I need some entries which are aligning to this data. So I pass in an array of tuples and with 3 values. So for example, like this, let's do it like this. The second entry is 3, 4, 5, and the fourth entry is that's 7, 8, 9, 10, so that we can see where these are. And now we pass in this complex dtype. And let's have a look at how f looks like. So now you can see that f looks like this. It has converted our array into the specific types. And if you look carefully, you see that each entry has now 2 floats because you have this dot as a representation. This is a syntactic sugar for you that you know that this is definitely a float. And this one has no dot, so this is an integer. So each of these entries is now one entry, one particle, if you want to look at it. So if I look at the first element, this will give you this 1, 2, 3. If you look at the second element, you get the 4, 5, 6, etc. And now you are asking yourself, where do I get this nice fancy syntax, like with this point where I do this dot y? Well, it works the same, but it's a bit different because this f now has no y attribute. As you can see, you have to use these square bracket notation. So you want to access the field y. And in contrast to the point where you only constructed a single point, and then of course you also expect a single value for y to be returned. In this case, you get all y values for all elements of the array. So this is the big difference. This is why I was talking about this think in a Numpy way, where you really think in arrays and not in single instances. You work really on a vectorized way if you want to be extremely performant. So this is the way you can access different fields. I can also access E. By the way, if you are confused, in Python, you can use either single quotes or double quotes. It doesn't make a difference. I used to use, I prefer to use double quotes most of the time, because then you can copy paste things to other languages. For example, Julia doesn't like this because Julia used this for single chars. And yeah, it's a bit more compatible. And just a side note. Okay, so if you want to look at the first element, which is 0, and then the energy of it, then this will be the syntax. Okay, let's have a look at some helper functions to create arrays, because we are sick of typing 1, 2, 3, 4, 5, etc. So helper functions to create arrays. Let's capitalize it. It's nice. Good. So the first helper function, which you will probably use a lot, is arrange. For example, like this. This will create numbers, like a given set of numbers in a consecutive order. I now place my cursor inside the parentheses and hit Shift-Tab if you're wondering. So this is this nice trick to open the docstring of the function. And you can see that it takes an optional start and then a stop and an optional step. And you can also specify the dtype or other things. So if I tell them that I want to have my C8 dtype or so, then I get complex numbers back. But the default is just let's look at the default. In this case, it should be just integer 64 exactly. So the other one which is useful to create some buffers or whatever is ones. So if you use ones, it will just give you the amount of ones you want. Zeros to create zeros, the same way, not very surprising. The cool thing is that they all have more or less the same interface. So instead of passing in a single number, you can also pass in a tuple, which now reminds you, hopefully, to this shape thing I showed to you. So if I pass in a 2 and a 4 as a tuple, I will get back an array which has this shape. So let's save it as A. So this is how it looks like. And if I look at the shape, you can see that it has the same shape as I put in. Sometimes you have already an array and you want to have another array with the same shape. So in this case, you could also say, also pass in the shape of an existing array to zeros or any other constructor helper functions, like np zeros a shape, which gives you, sorry, zeros, you already have ones like this. It will be, of course, recognized because this is just a tuple. So this is the interface connection you have there. If you want to be really, really fast and don't bother about the values, you just want to have a piece of chunky memory which you can work with, you can use the empty function, which will just give you random a contiguous piece of memory in your computer, but it will not initialize the values to any value. So in case of zeros, it will allocate this. So it will create this empty thing, and it will go through and set everything to 0. Or in case of ones, I set everything to 1. In this case, it's really just a memory. So you might see my whatever here, what is left over from the operating system. Yeah, some people use this to mine things, information which is left over in memory, malicious things mostly. Another nice helper function is the I function. This is called I because it resembles this I symbol, which is the identity matrix. So this gives you a nice identity matrix, which you can use to do your matrix calculations. Linspace is very, very useful. There you define a start and stop value and the number of items you want to have equidistantly calculated in between. So in this case, I have 10 values, which are almost, of course, equidistant because of the floating point nature. And another thing, if you don't want to pass things around like shapes, I showed to you that you can do something like A zeros and then give me zeros with the shape of A. There are utility functions which are called underscore like under. So like if I do this, this is basically a syntactic sugar, if you want to call it like so, to call zeros with the shape of A. So this might be also useful sometime. So you don't have to type dot shape always, but you have to type zeros like. All of these functions also take the dtypes, as I showed to you. So let me show it to you once more. Like if I tell you I want to have really tiny integers like this in 16, then I get like this. Okay, let's talk a little bit about random numbers. I hope it's not too slow and not too fast. Just interrupt me, Enrique. There are any complaints. Random numbers. Yeah, so actually also Max pointed out we should do it the right way. And we used to use this really sloppy random number generation in our presentations, which we never use in our production code. So let me switch to the correct way to do this. Many people just do something like this, random and then random, and generate some random numbers. This is, of course, what you can do, but this is not reproducible. So if I save this notebook now and hand it out to someone, every time he runs this, it will give you another number. And we want to have something which is reproducible because we are scientists, of course. And what we do is we can generate a random generator for us with a specific seed. So let's get the default random number generator with 42. I save it as this RNG object, and I bet with you, I hope I will not lose too much money, if you execute this on your machine right now with this default random number generator seed. So here's the object I created with the seed 42. This means that this defines basically the starting point, and every consecutive call is then determined. So if I execute this cell and this next cell again, it will always give me the same numbers. However, if I, of course, generate another set of numbers, like this, I will get other values, because otherwise it wouldn't make sense, right? You get always the same back. But these two executed in the same order will be always the same. Yeah, that's now quite interesting because, oh, sorry, big mistake. Of course, always use your RNG again. So here I create my RNG and then I use my RNG object. Now it's safe. Okay, here you can see I'm executing it again and again, and I get the same. And you will also see as the first element 0.773, blah, blah, blah. And the second call you will see as something like this. Make sure to call it like this. So this is very, very important. You can generate all kinds of stuff here, integers. For example, from 1 to 10. So this integer function is very nice to do some dice rolls, for example, or something like this. And you can give it a shape like 2 to 10. So this means I will now roll a dice with 10 sides. And it will give me an array back with the shape 2 and 10. So these are basically 20 dice rolls combined to 2 sets of rolls, basically. The same can be done with with other random generators like this, this will give you random numbers with the same shape. Again, because I'm using this random number generator with a predefined seed, this should be always the same. So whatever you put in, you should see the same numbers. There's also this helpful uniform thing where you can define a uniform distribution with the given parameters and the number of items. Yeah, and of course, feel free to hit tab and explore what else it can do. There are other functions like Laplace and multinomial, etc. Okay. Now let's head over to broadcasting. Broadcasting is a big thing in Numpy, and this is something which people always confuse a little bit how it works. But I think I have a very good explanation. So over the past years, I managed to figure out how to explain it the best way. So let's create first two arrays. The one is 1, 2, 3, 4, very creative. And the other one should be 5, 6, 7, 8. So these are now two arrays. Let's have a look at them again, just to make sure. Okay, so as I said, if you do something like G times H, you will get this result, which is then multiplied element by element. So 1 times 5 gives you 5. 2 times 6 gives you 12, etc. This works because they have the same shape. But what if I try to multiply G, for example, with an array of a different shape, for example, only 3 elements? Then Numpy will complain, and it tells you this value error, which you should remember from now on. Just listen to this broadcast message. Operands could not be broadcast together with shapes 4 and 3. So this means that Numpy doesn't know how to multiply two things with different shapes. This is basically what you get here. So something is wrong here. And there are some broadcasting rules which you can quite easily remember. I paste them here. Oops. Let me grab the rules so that we can go through them quickly. Oh dear. This is when okay, it doesn't work here. Broadcasting rules. I'm sorry. I have some difficulties with my copy paste thing. Okay, let's go to the warming up. You should be, I copy it over here. These are the rules. Of course, these are also in this warming up notebook. So let's copy paste them here and go through them. Oh, that worked pretty nicely. Let's have a look at here. It's nicely formatted. Okay, so the Numpy broadcasting rules. So it compares the shapes element-wise, starting with a trailing dimension. And then if two dimensions are, two dimensions are compatible if they are either equal or one of them is 1. Otherwise, you get a value error raised that frames are not aligned or something similar. This message has changed over the past Numpy versions a little bit. And the size of this successfully broadcasted array is the maximum size along each dimension of the input arrays. So I put here this example, which we will, let us have a quick look at this, because this is how it can be explained quite nicely. So the first rule is the shapes are compared element-wise. So imagine you have an array A, which has the shape 5, 1, 4, and 1. And your second array has a shape 7, 1, and 5. So you shift everything to the right, and you compare the trailing dimensions. So in this case, the trailing dimensions are 1 and 5. Then you look at the second rule. 2 dimensions are compatible if they are either equal or one of them is 1. So in this case, one of them is 1. So that's fine. And this will then take the largest value. So in this case, 5. The next one is 4 and 1. These are also compatible because one of them is 1. So the resulting shape will be 4. And in the third shape from the right, it's 1 and 7. So it will be 7. and then you have only 5, so it will take the 5. So this will be, if you do an operation with A and B, whatever it is, a plus or times or whatever, the resulting array will be this one. We will now have a look at specific examples, just to see it a bit easier. So let's create array 1 as a Numpy array, and now we create a nested one with 1, 2, 3, and 3, 4, 5. And the second array is now a Numpy array with a nested one and a nested 2. So array 1 looks like this, and array 2 looks like this. You see it right? You don't need classes or whatever. This is really just a nested array. I made it so that the shapes are really like this, 2 and 3, and array 2 shape is 2 and 1. So now we can do this rule again. We shift everything to the right. So this is not a big deal because both of them have the same number of elements, so we can just look at them. So if you do some operations on them, then the broadcasting rules will compare 3 to 1. They are compatible because one of them is 1. So the resulting shape will be 3 on the right side, and the second dimension will be 2 because they are compatible. They are the same. So let's try this out. Array 1 times array 2. It worked. Let's save it as array 3 and have a look at it. And as you can see, the shape is now 2 and 3. So this worked, obviously. Just print it again so that you can see what happened here. Yeah, and why is this useful? Well, sometimes you want to create some structure, for example, for an image or for processing, or a kernel for image processing, or whatever you want to do. And you use something like a gradient or so. I mean, so I can, for example, create 20 numbers, which are consecutive, reshape it, 4 to 5. And now I want to, oh, sorry, I'm lost in the, yes, maybe I do a bit of another explanation first. Let's save it. That's fine. Okay, let's have a look at this. If I now multiply this with another array, let's multiply this with 5 elements, like this, you will get back this result. So this is just to show you that it now figured out that you want to multiply each line, basically each subarray, with this array. So this is how the broadcasting rules are working for you. I hope this makes sense. This needs a lot of practice, but if you keep these things in mind, then you can really nicely guess the resulting shape, and this will help you if you want to create your structures which you are working with when you are writing your algorithms. We will discover this in the exercises later, and I really have to speed up because we also have a few exercises to go through. Maybe one more thing, which might be, no, you know what? You can, I think if we go to the exercises, because otherwise we will not finish it anymore. Maybe we can squeeze in some things in the pandas lecture either. Okay, let's go over to the exercises. And now we want to use all this stuff we have learned. And we go over to this one. So let's see Numpy in action. Exercises. So I think I will do this in this notebook here. It's easier with the solutions. We have to save time. I completely overestimated how long it takes when I make it slow. I'm really sorry. I hope you're not bored already. Okay, so now I open this Numpy exercise solutions. In this case, it will be now a little bit faster, but I promise you I will commit it to the repository so you can look at it. You can now still follow along and type it down. in this case, the first exercise is we have an array with 5 elements. You can just write this down and pick 5 elements as you like. And we want to extract the integer part of this random sample. So there are different ways. So what does it mean, the integer part? I'm only interested in 23, 42, etc. So this is some common thing which might happen in your scientific research time. So you might do something like, probably this is the most complicated one, but I start with that. You might want to think about subtracting from A the A modulo 1. This will give you, of course, the integer part of it. You can also use the functions like floor, which will round them down. You can also do ceil and subtract 1. You can do the truncate when you know that the values are all positive, or you can use the casting to integer, which will just drop the commas basically. This is what we already saw when we were typecasting them. And I want to show you this really dumb exercise just to show you some numbers, how well Numpy does here. So if I create now a large array with this random number generator uniformly, so these are now 10,000 elements. And if I time these, so let me time all of them. I run this time it macro. Then it will run now several times, and it will give you the result, how long it takes on average. And you can see that this operation is really, really slow. It is slow because this modulo operator, which takes the remainder when you divide it by 1, is really slow. And then you have to, again, also subtract. The subtraction is really fast, but this modulo will be slow. So here, in this case, you need 110 microseconds. Floor is really fast. We do it in almost 3 microseconds. If you do a ceil and subtract 1, of course, it's really dumb. There you can see that the subtraction went into it, so it takes longer. Truncate is similar to floor, but it always truncates to 0, so you have to be careful whether you want to have floor or trunc if you want to do such an operation. But the most important thing is that casting is really the winner here. It's extremely fast because casting is always good. So casting can be done on a very low level side, and no real operations are needed there often. So this is how you can do it more performantly. So whenever you want to convert large data sets to another type, just or want to truncate things or etc., just think about casting first. The next thing is to create a 5 times 5 matrix with 5s on its diagonal. I already gave this hint that you can use the I function. And I also show you the solution. There are different solutions to this. Again, we will discover these a little bit more. So you can see I created an I and multiplied it by 5. So again, if I just do an I5, I get this identity matrix. And when I multiply it with 5, it will multiply every single element with 5. And of course, so that we have zeros on the other side, only the diagonals are 1, then now we get this. Let's have a look at this discussion, because if you use Numpy, performance is always crucial. So if you time this, you already see the results, right? I should hide them. So let's time the first one. It takes about 800 microseconds because it first has to create this matrix. Now I took 1,000 elements instead of just 5 on the diagonal, and times 5. So it has to create this. It has to allocate memory for 1 million elements. It has to multiply it by, it has to initialize them to 0 and the diagonals to 1, and then multiply it by 5. So this is how long it takes for a computer. I can do a kind of a trick, which is this Numpy multiply. So I'm not calling this times, but I call multiply. I give it a and 5. So these are the 2 operands. This is just another way of calling it. I do this because here I have the option to tell Numpy to reuse my A array. So this is what I told you in my last presentation, that sometimes it's, if you know that you don't need the original array anymore, you can just write back the results into this array. So in this case, I specified it as an output array. So it should avoid creating a copy. But in fact, in this case, it's not really worth it. So sometimes it's better. In this case, it's even slower. because of whatever. So it is just to show you that there is a method to avoid. So at least it consumes less memory. This is something which might be crucial sometimes when you work with large data set. Another solution would be to create zeros, and then which is also very fast, and then use this diagonal indices from function. So this is something which takes only almost half of the time. I show to you what it does. Diag indices from, and now create something like np ones 5. Value error. Let's take a. I think I overwrote a. B zeros. Okay, we just picked whatever array we want. Maybe it's a bit too large. I'm sorry. Let's make it smaller. So this function gives you the indices of the elements which are sitting on a diagonal. So this makes it fast because you first create these zeros, which can be done really quickly, and then you only set the elements to 5 which are sitting on the diagonal. So in contrast to this example here, or this other one, where you really multiply also all the zeros. You have to imagine you only have like 1,000 diagonal elements, but you do the multiplication 1 million times. Here in this case, you really tell Numpy by this fancy indexing that it only should set the elements to 5 at this very specific places. So it first has to create the zeros, allocating 1 million elements, and then walk through all the diagonal elements and set them to 5. Okay, there's another method called npdiag, which will create a diagonal matrix. So this is also, as you can see, very fast. And you can even use this once times 5, which is for some reason even faster than this. But yeah, well, if you look at the errors, then probably they are almost the same. This is just to show you some other things. And since you had some questions about number, I thought it would be nice to also show you some number versions. So in this case, I just took the fastest one, which was this one from above, and I put it in a function where I can specify n and value, and I put on top of this number ngit function. And if I call this, you can see that it takes the same time, so I don't get much out of it in this case. So this is where number doesn't give you anything. But I also tried to write the algorithm by myself. So in this case, I used Numpy in a simple Python function to create a matrix with zeros. And I'm walking through the diagonal elements and setting them to the specific value, which is passed in here. So this would be very, very slow if you used Python. But if you put number ngit on top of it, then it will be very fast. As you can see, I can compete with the Numpy implementation in this case. So it's basically the same time. So this is the power of number, where you can really just write your algorithm with really stupid for loops, as you would do in C, and have all kinds of customizations. You can do here ifs and theirs and loops, and then even more for nested stuff. And most of the time, you will end up with really, really nice implementations like in Numpy. Okay. So now I would like to show you the example which I pointed out in my presentation today with this numexpr. This is where the power of numexpr comes to shine. I create 2 random arrays, A and B, and the exercise is to calculate C, so that C is given by this. So all the elements of C is given by this expression here. You can see it uses tangents and multiplication, and then a power of, etc. for the same element. So it's basically an element-wise operation. And if I write this function with Numpy, then it's Numpy tan A times B minus a to the power of B. So really straightforward, nothing fancy. If I time it, you can see that it gives you 17 milliseconds. And in contrast to numexpr, which takes only 5 milliseconds. This is the reason why you should use NumExpert whenever you know that you don't need this intermediate stuff and you are doing things element-wise. Because in this case, as I already mentioned, this call numpy tangents a will create an intermediate array of my tangents values, then multiply it with an array. So this expression will also create another array. Then this will be calculated because of the precedence. This will be another array, and then everything will be again calculated because of this minus side. So this needs again memory allocation. So we are doing a lot of pushing data in the memory. So what about the Python loop? Well, I also wrote a Python loop just to show you how slow it is. So here with the NumExpert, we were at around 4 or 5 milliseconds. If you do this in Python, you are at around 2.2 seconds. So 3 orders of magnitude slower. But, and now comes the funny part, I just put this number JIT on top of it, and I now need only 15 milliseconds. So I've not changed anything of the code. I just put in this number JIT, and I get this really nice result. And now I can even use this trick with this NumPy before, where I said that I just write my calculations back to the original array, so that I'm mutating it. I'm reusing the memory I already allocated. And this mutated version is even faster. So here I also wanted to show you that the first call is always slow. So in this case, here's my function which mutates the original array. So it writes back to A, the result of the calculation. And as you can see, the first execution takes 50 milliseconds, whereas the second execution takes only 8 milliseconds. And the reason is because in this step, all the compilation and type inference stuff and everything is basically executed in number, and it takes a lot of time. But the second call, number sees, okay, you are calling the same function with some values. It doesn't care about the values, but it does care about the types. So it will see that A has a dtype of float 64 and B has a dtype of float 64, and it already has a version of this function compiled for a 64 and float 64 value, so it will reuse them. And here's the summary. Your mileage may vary, of course. In this case, the winner is NumExpert. Okay. So another exercise, again, feel free to just sit down later and go through the exercises by yourself and explore how it works. I will just now show you the solutions and discuss with you. So this is given 2 arrays A and B, check if they are almost equal. So this means that we have to check if we subtract them, if the absolute value of the result is lower than some kind of threshold we check. So what I do here is I create these random numbers with this many amount of items. I do 2 copies. You can call this copy, so you get a real copy of it. So now I have 3 arrays sitting at different places in my memory, and I make them. So I change the last element of B to be 23 and the first element of C to be 23. So now they are different. In B, the last element is different in contrast to A, and in C, the first element is different. I just showed this to you because there are different algorithms which check if things are equal, and we can exploit this. So there is this NumPy allClose function, which you can use to compare two arrays with each other. And I hit Shift-Tab when I place the cursor inside the parentheses, so I can look at the doc string. And as you can see, it takes these A and B. These are required, and these are optional parameters. And there you can see that there is a relative tolerance and an absolute tolerance, and also how to treat not a number values. I just called it with the default values. So what it will do is it will compare elements side by side for each one, and it will see if the difference between the 2 elements is less than these 2 specified tolerances. It takes 4 milliseconds to compare A to B, where the last element is different, and it takes also 4 milliseconds to compare A to C, where the first element is very different. So it seems that it doesn't make any difference whether the first element is differing or the last element is differing. In principle, if we call all close, we only want to know if they are different. So you can imagine that if you iterate through all the element pairs and you find the first one which is non-matching, then we can basically break our loop and return immediately false. But this is not the case in this case. So it somehow it seems it computes every element and then decides if it's okay or not. So let's write our own algorithm. And in this case, we really do what I just said. So we wrote this rclose function. We have the element, we have the array A and array B. We also define this tolerance just to be more parametric in this case. And what I do here is really just iterating over I in range of length A. So this will give me the index. So in the first iteration, it's 0, then 1, 2, etc., etc. And then I calculate the absolute value of the differences between the same elements of the two arrays. And if they are greater than my tolerance defined, then I immediately return false. So I don't check all the elements, I just return false. Okay, let's time it. And as you can see, it only takes 800 microseconds. So it's like four times faster than this rclose function when I compare it to B. Remember, with B, the very last element was different. If I compare it to C, where the first element differs, it only takes 200 nanoseconds. So obviously it works. It started to compare and it realized, okay, these are not differing, so I don't care about the remaining 1 million or whatever elements. I can stop it. So this is why Numpy is so useful when you need something which might even be really tailored to your use case. So you might analyze data where you know that you expect some deviations at the beginning, or you expect some deviations at the end. And Numpy and SciPy and all this stuff give you really nice tools which cover some use cases, but often you need something custom. And sometimes it's much more easier to just write your own stuff. Other times where you think that it might be generally applicable, you would just extend a library and bring this function in. Okay, here's another exercise to create this following matrix. This is basically a gradient matrix. It's often used in also in image processing, for example. And this should highlight the broadcasting things, which you have learned before. I'm creating here ones with this one. Let me show you what the first one is. So this we already saw. And this NP A range 1, 7 will give you this array, so 1 to 7. And if I multiply them together, then you can imagine that it takes this array and then multiplies it with the first row, and then with the second row element-wise, and the third row element-wise, etc., etc. And the resulting is this, exactly what was asked for, at least. Here it seems it's integers, we have floats, but of course we can also recast it to integers if you want to. Now let's have a look how fast this is, because this is always the question in Numpy. Is it fast enough? Am I using the memory efficiently or not, etc.? So the solution I showed to you takes around 6 microseconds. You can do this trick with saving a bit of memory by reusing the array A, which makes sense in this case because the ones you create here above are really only used as a container, and there is no need to keep this alive or whatever. We can just really reuse this and keep this and put the values back. And as you can see, indeed, it gives you a little bit of performance, but in this case, also the computation is, well, the allocation is not really worth it. So no big benefit here. But there is another method which makes it even slower. This is using the ones, and here I'm using this new axis thing. So instead of creating this ones, which is 2-dimensional, I can create ones with a, let's make it a bit smaller so that you can see it, like this. So this will give you just a single-dimensional array with 5 elements. And if I now use this trick where I say I want to have each element in the first axis, and then I want to add the new axis, use this syntax. This will reshape your array. So maybe I show for the shape once 5. So this was our first one, and the shape of it, sorry for the typos, is 5 and nothing else. And in this case, the shape is 5 and 1. So it's really two-dimensional. Also, although it doesn't really look two-dimensional, but it's two-dimensional. You can see that it's nested. And because it's nested, if I now multiply this with something like this, then it will expand along this new axis because of the broadcasting rules. So remember that the first one had a shape of 5, 1, and the second one had a shape of 5. So the broadcasting rules will give you a 5, 5. Instead, if I just would do a shape of 5 multiplied by a shape of 5, it will do just this element-wise thing, and I will get only a single array. Yeah, I hope you understand this. Otherwise, just try around with this new axis. Also, here it's explained again, so we just walk through it in the first notebook. Yeah, there is also another thing, because I told you that we are using this numpy empty if we don't care about the elements when we override them anyways. And this is the case. So in this case, we can really save a lot of initialization time by not initializing them to 0 or 1 or whatever before, but just taking a chunk of memory and overwriting them with this numpy range. So it gives you a speed of 3 times in this case, which can be huge sometimes. So what about number? So remember, we had something like 2 microseconds for the most performant one. Number, we can sit down and write our dump function by ourselves. So we just create this matrix. We do a for I in range m and for j in range n, and matrix ji equals 1 plus 1. Yeah, it takes 1.3 microseconds, so twice as fast as this one, which should be already quite performant, but we beat it with number. Yeah, we can even make it a bit faster if we explicitly tell a number to use an integer type for our empty matrix here. Because as I said above, in this case, we don't care about the types, but it can be beneficial to use a different type because some operations can be faster when you are doing integer. So integer multiplication is different from float multiplications, etc. So there you can have different times. As you can see here, I have something like maybe 15% speed gain. Okay, I think we will not make it through all the exercises. So I'm asking Enrique about the status because I have not have any Slack running here in front of me right now. If there are any questions or, well, if it's too slow, I think it's too late because I already talking for almost 1.5 hours.
Yeah. No, so basically there were a couple of questions that they were we were able to solve, and then due to the live streaming, I didn't want to interrupt also the live streaming difference. So as you prefer, Tom, I mean, you can continue or...
Okay, then I would like to continue and maybe just switch over to the nearest points exercise, which I really like. I mean, it's binary data is anyways an optional thing. This is, I'm not sure if there are too many people who really want to parse binary stuff, but you can have a look at it if you have some use case. There are some other nice exercises where you roll here some dices, etc. So just have a look at it. We are creating checkerboards, etc. And so on. So there you will learn some intrinsics of NumPy and where to use number, where to use NumPy, etc. But we will also have this number lecture to learn even more about it. But last but not least, I would like to show you this nearest points, which is much more real world example maybe, which you might find useful. So the exercise here is given an array of points in 3 dimensions. Find the nearest point for each one. So in this case, I generated 500 points. So I just call them points. I don't need this x, y, z right now. I just imagine these are points. And this array contains now 500 of them. And I want to know the nearest point for each of the points. So if I look at the first point, then the question is, what is the nearest point of all the other points given to this? And then the second one and third one, etc., etc. So this is basically the question. And the nice thing is you can really nicely do this with Numpy. Also, maybe not the most performant way in terms of memory, but it's just a few lines of code. And let me show you the solution. The solution is just these 3 lines, and I find it quite nice because the exercise itself looks a bit complicated first, but when we discuss now this solution, it will make sense, and it's quite natural, and it resembles the way of thinking when you work with NumPy data. So in this case, the solution is just the indices of the points. So for the first point, the nearest point is the second one. For the second point, the nearest one is the first one, of course. The third point, the nearest one is the fourth one, and then the second one. So this is how you interpret this solution. This is what we are looking for. So we are looking for the indices, actually. Okay, let's look at this. For the sake of clarity, I only work with 4 points now. And we look at the shape, you can see that we have 4 points with 3 dimensions each. And the first thing I did is I reshaped it so that it's basically a blow up of the array. Instead of having 3 points as a subarray, basically in one array, I now put them in a nested one. And this is needed because I want to do some broadcasting tricks on it. So you can see the reshaped one contains the same values, but now they're doubly nested. And this is now our shape. So my shape before was 4, 3, and my shape now is 4, 1, 3. Now I have this extra dimension. And the reason I did this is now I can calculate the differences. So basically the results, this results in the vectors pointing to each other. I can subtract the reshaped points from the points, or otherwise around. So now I have in each subarray, I have the pointer vectors between each point pairwise. And here you can see again the broadcasting rules, how they are applied. So my initial array had 4, 3 as a shape. My reshaped one had this extra dimension, which is basically empty, 4, 1, and 3. And then you put them above each other, if you remember how we did this, and you compare the last one. So the trailing dimension here is 3 and 3, so the resulting is also 3 because they are compatible. The next one is 4 and 1, so you pick the 4, they are compatible because they are not equal, but one of them is 1, and the last one is 4. So now you have in each array, you have the pointing vector to each other element. You can also see that the first one in the first entry is 0, 0, 0 because they are pointing to each other, and the second one and the third one and the fourth one is also 0, 0, 0. And now I can use the Linard norm to calculate the distance, basically, or the length of these pointing vectors from these differences along axis 2. And this means that now I am operating really in the deepest dimension of this array. So I'm calculating the length of this vector, the length of this vector, and the length of this vector. So these 4 lengths, which it calculates, are now represented in this row. And then the next one, so all the 4 vectors, the lengths are calculated in the second one, etc., etc. So what you see now here is for the first point, the distances to the 4 points are 0 and 0.3, 0.5, 0.8. So of course the distance to itself is 0. And now we want to have the closest one. But if you now would call something like the minimum, give me the minimum of each subentry, you will always get 0 because the closest point is always the point itself. And this is, of course, not what we want. So I'm using here the trick that I'm setting the diagonal elements of the distances to infinity. So here, this we all have already seen, the diag indices from distances. I use this as a mask, and I set all the elements of distances to infinity. Now, the resulting array looks like this. So I have now infinity and then some values. And now I can call this numpy argmin, distances on axis 1 in this case, and this will give me the answer. So the first point is closest to the second one, the second point is closest to the first one, and so on. There is also this scikit-learn package, which you might know. There is this method you can call, so this nearest neighbors implementation, where you can fit your points and use this k-neighbors implementation. This will give you the same result. And if you compare the times, our implementation with NumPy is much faster, like 7 times faster or so. Now you might think, okay, then let's use our own implementation or make a pull request to to sklearn and implement this instead. Now it's not so easy because this is a much more mature algorithm. And if you blow it up, your array, for example, to 1,000 elements, you will see that our implementation really struggles. So here we use 23 milliseconds, and there you only need 1 millisecond. So it always depends on your use case. If you work with really tiny data and don't care about memory, then probably this is the way to go and don't use these nearest neighbors. Or there's, of course, those other algorithms which can do this. All right. I think I finished now. I almost have no voice anymore.
Okay, perfect. So thanks a lot, Tom, for this nice hands-on overview of the NumPy library. At least myself, I have learned a lot of things that I didn't know. So.
Oh, that's good to know.
So maybe one general question that it was raised at some moment, but you might be too fast, and it is interesting to explain it in live. Which is the difference between np.arrange and np.linear space?
Okay. Yeah. So np.arrange is really used to create something with a given step size. So if you want to have something like how would I? So if you put it like 10, then you will get these 10 elements, which are, of course, in this case, equidistant. But sometimes, for example, you want to sample something like plot a function or so, and you need a specific number of values between two limits. So if I now want to have something like 10 elements between 0 and 1, I could do something like this, but now the end is not really defined. So I want to have 1, for example, in this case. So this is where linspace is then really helpful, because there I can really tell that I want to have 10 as the starting point and 0 as the end point and 0 as the start point. If I want to recreate this with arrange, it will be a bit nasty, because here you have to think about like this. You have to start by 1.1 because you have the step size, etc. And if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, now I have 11 elements. So you have to do then something like this, but now you don't have 0.99, etc. So I hope this makes it clear. So in a lot of languages, like also in Julia and MATLAB, etc., you have usually these two functions where you either define the step size or you define the number of elements you want to have equally spaced between start and end points.
Okay, perfect. So we still have time for a couple of questions, and there are some popping up in the Slack channel. So, for example, which is the difference between the NB-JIT and the NB-NJIT?
Okay, so imagine a function. I call it like foo, and I do something like return x or so. I probably cannot do a version which is maybe, let me see, something like this. Let me construct a quick function. So if I do it like this, let me do a JIT over it. So if I do a number, JIT, import number. Okay, S and B. Okay, this still works. This is a bad example. I cannot come up with an example where it's space now. So ngit means, so whenever number tries, so JIT is the default one. Whenever number tries to compile this function and it encounters an error, it will fall back to Python mode. And I tried to force it to not be able to compile this. I'm not sure what I should call here. Or maybe I, oh wait, I think I know what I return a dictionary. Dictionaries are always nice. X is X or so. Dict X equals X. Oh, sorry. Oh, this still works. Oh, damn it. Okay, yeah, this is live coding example. Okay, if you put in ngit, long story short, if you put in ngit, you always get an error whenever number is not able to make a performant version of your function. If you don't put an n here, then then you never know if it actually compiled to a performant version or not. I'm sorry, I cannot come up with a good example.
No, but perfect.
But
thanks.
yeah,
Thanks
I think you get it. So yeah.
Number got much better with supporting more Python features, so it's really hard to create an example where it cannot compile.
Yeah, it's probably maybe if I use some class foo or whatever. Okay, you can proceed to the next.
I think one example is a list of different data types.
Oh, okay, yeah, that's of course a great one. List true and false. Oh dear. Maybe some. Is there another question in between? I try to.
We have basically solved all of them.
Oh, there you go. Sorry.
And in any case, also if I think that if anybody has any kind of doubt or question while resolving the exercises, they can post it in the channel, and
yeah, sure. Yeah,
we'll
just
address
me.
and later.
Of course.
So
let me come back very quickly. So here I made a dumb mistake that I did not execute the function. So of course it doesn't compile if I just call it. So here's, okay, I think some of the examples before would also have worked. So here you can see I'm calling foo with 23. And this is something which should usually work in Python. So if I do the sum list true false Python sum list, let's do a star in it. Okay, this also doesn't work. Whatever. But anyways, this is the typing error you get. So failed in no Python mode. This is how it's called. And if I now calculate it with if I only put JIT, then I get the regular error because it has this type error. Yeah. Okay. I have no good example here, but you get the point. I always recommend to use ngit in case you want to enforce number usage.
Okay, so nice. Thanks a lot once more, Tom. So I think that we can close the session here. There's no more questions that we can raise. So I mean, in any case, we will be able to answer later in the Slack channel. So thanks a lot, everybody. We'll stop here for the lunch break, and then we'll return in the evening. I think it is 2 p.m. Central European time, and that's it. So thanks once more, Tom, and see you later.
All right, I will upload the solutions to the exercises so that you can.
Also, so everybody, you will need to do a Git pull to obtain the.
Yeah, it just takes a few minutes.
Yeah, not immediately, of course. Thank you. Bye-bye.
All right. Bye-bye.